Okay, AP Chem, let's take a look at exercise 6. Um, Before we do that real quick though, I do want to have you erase one little thing on here. This is exercise 5. Where this says kilojoules per mole, um, this one is not necessarily correct. These units are incorrect on both 5 and 6, so please cross them out. The reason why is number 5, we did not use one complete mole of reactant to do this. All right, so this is negative 5.6 kilojoules for the specific circumstances, which is 100 milliliters of 1 molar and 100 milliliters of 1 molar HCl. Same thing's going to be true here. I'll show you later on when we're going to do the kilojoules per mole of reactant. This is not one of those cases for either one of those. So I apologize for that. Let's look at number 6, okay? So number 6 states when 1 mole of methane CH4 is burned at constant pressure, 89 or 890 kilojoules per mole of energy is released as heat. Calculate the delta H for the process in which 5.8 grams sample of methane is burned at a constant pressure. Now you might be asking yourself, why in the world is this constant pressure mentioned? Well, it's kind of the default setting for calorimetry. This calorimeter has no seal lid on it, so when we do a coffee cup calorimetry, we either will put a plastic lid on the top with an opening with um, a thermometer through it, or we'll have it open. Okay, we do lose a little bit of heat if it is open, as opposed to this thing we call a bomb calorimeter, which is a closed system. The main difference between the two is when you heat things up inside of a box, it tends to increase pressure, which changes lots of things with the energy. So we don't tend to use this. All right, we tend to use this. Plus, this is a lot simpler. We can do it in our lab. We don't have the equipment to do this. These are the most common problems that we will see in calorimetry. So I just wanted to point that out so you aren't scratching your head. What does that mean? So here's what we're doing. We're burning 1 mole of methane. All right, so here's my chemical reaction. CH4 plus O2 yields H2O and CO2. Okay, and we need to balance this. Okay, so now I have 4 and 4. I have 2 oxygens plus another 2, so I'll put a 2 here. So there's my chemical reaction of this process. We have to do this because we're going to start off with a certain amount of 55 or 5.8 grams of methane. Okay, so here we go. We have um, all right. So what it's asking for is what is delta H. Okay, delta H, okay, is enthalpy, and we commonly refer to it as heat. So what is the change in the heat energy that is being transferred? Okay, so when I look at this, I have a quantity of CH4 in 5.8 grams. However, I don't have a unit of grams in my problem. I have moles. All right, so you'll find yourself doing this quite often, is changing the mass of something into moles. Now, this may seem silly. Why don't they just give it in moles? Well, here's the deal. When you're in a lab, uh, we don't have a mole cup. We don't have a measuring tool for a mole, but we do have a scale. So when you are doing things in the lab, everything you start off with will be in grams because you're weighing it. All right, so 5.8 grams. Um, and we're going to divide this by the molar mass of CH4, which is 16. And that will equal 1 mole. And we probably should put our units up here so we keep track of everything. All right. And this is actually CH4 as well. And this will give us 0.3625 moles of CH4. Now, you may want to leave these in your calculator because it's going to make it easier. You get a little bit more accurate number at the end if you don't shorten it or do sig figs at this point. This is fairly simple from here. We have our amount of energy that's going to be released with 1 mole. 1 mole will be 890 kilojoules. So all we have to do is multiply 890 kilojoules over 1 mole. And divide out our units. Okay, multiplying 0.3625 times 890, and we get 322 kilojoules. In this case, it looks like we have 2 sig figs right here. So if we're being accurate, it's 320 kilojoules. Okay, so useful tool there.